Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss the Dormand Prince method. So in this topic we will derive and describe the adaptive Dormand Prince technique. We will look at an implementation and see two examples thereof. Now, given the approximation tkyk, the fourth order Runge-Kutta method sampled the slope 4 times at 4 different points. Now you're going to notice that 2 of those samples were somewhere inside the interval from tk to tk plus h. Once we've got those samples, we then took a weighted average of these slopes to best estimate the value of the solution to the initial value problem at the next point. Well, Dormand Prince more or less does the same thing, except more often. It actually samples the slope 7 times. And you'll notice that it samples the slope at 0.2 times h, then 0.3 times h, and then 0.8 times h, and then plus 0.8 times h, and the last two sample at the right-hand endpoint, tk plus h. Now, you're going to notice that the samples are always linear combinations. So for example, when calculating S2, 1 plus 3 is 4, so that's actually a weighted average of the first two slopes, S0 and S1. When we calculate S3, notice that the coefficients of S0, S1, and S2 are 11 minus 42 plus 40 all over 9, and we see that too is a weighted average. So just like with a fourth order Runge-Kutta, we are taking weighted averages to calculate or evaluate the slope at the next point. Now, while we are calculating the last slope S6, it happens that the most accurate approximation is actually that value that is calculated there. So that's actually quite nice, because while we are calculating these slopes, we automatically are calculating the optimal approximation of the value at the next point. This is the less accurate approximation, and so now we have two approximations, y and z. Y is less accurate, z is more accurate, and these are independent of each other, and so therefore the accuracy of one can be used to determine the accuracy of the less accurate version. So the absolute value of z minus y is a good estimator of the error of y. Now, something that's very important here, because I haven't actually described the error, is that the error for the approximation of the more accurate value, z, is order h to the 6th. Now, why is this important? Because the literature refers to this one as being the 5th order approximation. Just like fourth order Runge-Kutta, is order h to the 5 for a single step, but if you repeatedly apply it, the error drops to order h to the 4th. So the more accurate approximation, z, is order h to the 6th. Similarly, the less accurate approximation, y, is order h to the 5, even though the literature refers to it as being 4th order. This is important because when we are estimating the error, we are only estimating the error assuming the current value is correct, and we'd like to get the best approximation of the next step. Consequently, from mathematical analysis, we are told that y has a single step error that is order h to the 5. Therefore, twice the difference between z and y is approximately equal to some unknown coefficient times h to the 5. We don't know what it is, but fortunately we don't care. We can solve for this unknown coefficient, or at least approximate it, by dividing both sides by h squared. Now, just as we wanted to before, we want to choose the ideal width, that is, a scaling factor times h, so that the error is exactly equal to epsilon abs times the width of the interval. So basically we want to find the correct value of a such that these two values are equal. We want the error caused by the current step to be no more and no less than the error we are willing to tolerate for an interval of width a times h. Solving this for a, well, a to the 4th, we have this expression here, so one of the ah's cancels out, and we are left with this. Well, we have an approximation of c up there, so we can substitute the approximation of c into this expression and take the 4th root of both sides. All right, so this gives us our approximation of the scaling factor that should give us the most appropriate width of the interval to use. All right, this implementation does require a few constants, and you will note that, again, we have a matrix there, but if we only give the first entry, C++ by default sets all other entries in that row to 0. Now you will notice that every single row sums up to 1. That is, each row has coefficients that provide a weighted average of the slopes in this case. Now, one thing that's very important, here I have a table or an array of the coefficients ci. Ci, which is actually the steps, is an indication as to how far into the interval we are approximating the slope. Then we are taking a weighted average of the previous slopes to update the y value. Now, normally textbooks multiply out the step size times each of the rows. So for example, the first entry is not 1, but usually 0.2. The second row is not 1/4 and 3/4, but rather 3/40 and 9/40. However, that's an implementation detail. The reason I'm showing this matrix, lower triangular, as a weighted average is because I want you to clearly see that every row is indeed a weighted average. Finally, at the bottom, we have the weighted average of the slopes that will be used to find the less accurate approximation. The implementation of this is actually not that much more complex. We need to calculate 7 slopes, but the first slope is already the slope at the point tk, and we've already calculated that and put it onto the queue for the slopes. So we're just going to grab that value off of the slope, off of the queue. I'm going to set z to be undefined right now, or initialize to the default value, but we are going to update z. All right. So now we're going to calculate the rest of the slopes, S1 through S6. We will evaluate the slope at some linear combination of the previous slopes. That linear combination or weighted average of the previous slopes will be calculated and set to the local variable slope. Now we calculate that linear combination from the previous table, and then we're going to set z to be the previous y value plus h times the step size times the weighted average of the previous slopes. We will now calculate the slope at that point that we calculated. We will do this 6 times, and nicely enough, the very last time we do that, it happens that that weighted average is actually the more accurate approximation of the two values. So whatever z ends up being assigned when this for loop ends is actually the more accurate approximation, which is nice because that means we don't have to do any more work to calculate z. However, we must calculate y now, the less accurate approximation, and that just requires us to take the following linear combination of those slopes. Now we have our less accurate approximation. With that, we can calculate or estimate the value or scalar a, and now we go back to normal. We determine whether or not this a indicates that we are sufficiently accurate or not accurate enough. Now on slide 4, we represented the calculations of the various slopes as follows. You will note that we have a linear combination of the previous slopes with very large integers, which may seem a little peculiar. However, this is useful in that you can sum up the coefficients in the numerator and you will see that they sum up to the denominator. What this means is that we are taking a weighted average of the slopes. Only once we calculate that weighted average do we multiply by 8/9 times h. However, in the implementation, you will notice that we distributed the division by the denominator across the sum. What this does is it ensures that the coefficients are as close as possible to 1 in absolute value. Only once we calculate the weighted average do we multiply through by 8/9 times h. And again, we've already calculated 8/9 times h previously, and so we are not performing any additional computations. You may, however, be tempted to do the following. This is going to be an interesting situation. You may think that this should give the exact same result as the previous version, but under certain circumstances it does not. The issue is that if h is very small, then the calculation of each of those terms in the sum may actually produce a denormalized number. What that means is that you're going to get a significant error that may be introduced. Also, if h is small and we are adding them one at a time to y sub k, then again we are losing precision. Interestingly enough, this did not actually occur to me as being a problem until I was trying to debug a submission by a particular student. So the intermediate solution, the one that we use in the implementation, is likely the best, the one that will introduce the least numerical error as a result of performing that computation. Now suppose we have the same initial value problem we had with the previous example with Euler-Hoyne. We're going to have the same h-min and h-max, 0.01 and 1, so that the initial h value is 0.1. However, now we're going to have a slightly more stringent absolute epsilon value of 10 to the negative 5. So here is the function and the approximations. You will note that the initial step size is 0.1, and we only allowed ourselves the luxury of at most doubling the step size. So you'll actually notice the first approximation is at 0.1, the next is at 0.3, which is 0.1 plus 0.2. The next approximation is at 0.7, which is the previous approximation, plus 0.4. And the next approximation is at 1.5, which is the previous approximation, plus 0.8. So up until this point, we're simply doubling the step size at every single point until we start reaching the curvature point where we need a slightly smaller step size. However, notice once we get beyond the bottom, then we get a slightly larger step size again. Now here's an important problem. We're having a maximum step size of 1. However, this can be a problem because we're approximating intermediate values using cubic splines, as you may recall. And consequently, these may actually have larger error if we have a larger step size. So we may actually want to restrict the maximum step size if we want accurate approximations between these points if we are using cubic splines. Suppose, however, we have a similar differential equation, but now one where the forcing function is discontinuous. Consequently, the error analysis which we relied upon to get Dormand Prince to work no longer applies, and consequently, if we use the exact same constraints at the discontinuity, h is made successively smaller and smaller because the solution is now continuous but not differentiable at the point of the discontinuity. Therefore, in order to try to approximate it to the acceptable requirement of an absolute epsilon value of 10 to the negative 5, h must be made arbitrarily small, in which case we hit on the lower limit of the h value, 0.01. Once we pass the point of discontinuity, h starts doubling again until it gets to a reasonable width as is appropriate for approximating the solution where the differential equation is not discontinuous. Following this topic, you now understand the adaptive Dormand Prince method, and you're aware of the calculations required to get these approximations of y and z. You also know how to take these approximations and derive the appropriate scaling factor A that will tell us the appropriate step size to use. You've seen the implementation and have seen 2 examples. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!